Hi, I'm Chinmay Gakar.
I'm Josh Campbell.
I'm Amar Kabesh.
I'm Dale Kim, and we are Group 2.
This is our embedded rover for 4534, and the goal of this class was to create a rover that could navigate a race track, a course, without bumping into the walls and autonomously reach the end of the course as fast as possible. In addition, the rover would have to run through the course a second time, hopefully faster than the first run, meaning it learned the track or mapped it in some way and then repeated it faster than the first run. Additionally, we had some other tasks which the rover had to identify a finish line and stop at the finish line, and also identify turn signals located on the track and obey speed limits found on the track.
For our project, our rover is started by a web server via input buttons. When activated, the buttons send messages throughout an Ethernet cable, and they'll go through this ARM board where they'll be picked up by a motor control task. Message queues are simply just a communication protocol where you can relay information between the system through tasks. The HTML page displayed here shows the web server that our group used to communicate with our rover. There's 4 buttons on here and 2 checkboxes. And for the first button, Simple Speed Run, it's just supposed to start the rover and have it go as fast as it can while still avoiding the obstacles. The button below it would stop it and just halt the current run. The checkbox above Simple Speed Run, though, is supposed to indicate that the rover is going on a second run of the Simple Speed Run. On the second run, the rover is supposed to have recalled its previous run and go as fast as it can, knowing where the obstacles are now in the course. As for the third button down here, Find the Finish, the rover is supposed to locate in the racetrack the finish line and get there as fast as possible. And Stop Rover would once again stop the rover. When having the loop track selected and clicking on Find the Finish, this will have the rover go on its second Find the Finish run, where it will look for a finish line while still recalling the data from the previous run.
When the web server sends a message to the ARM, it will send a message to the 2 picks, checking to see if they are on or off. The sensor pick on the rover itself will be checking each of the 3 sensors on the rover and sending information back to the ARM. In that time, the ARM will interpret the information sent from the sensors and relay motor commands to the motor pick. In our original design, we were going to have a master pick on the rover and a ferry type wireless pick on the ARM side. But unfortunately, we had issues relaying UART information when the XB wireless communication was connected, and we had to remove that from the design.
For our project, the central brain of the entire rover in operation was this ARM processor board. The reason this was the brain is because it runs and operates at a much faster clock speed than the picks on board the rover and can make decisions much more quickly. Additionally, the ARM runs on a real-time operating system. And a real-time operating system is an operating system that is intended to serve real-time applications. What this means is that it can process data very quickly as it receives the data, for example, our sensor data coming from the picks, and can react to it quickly. Additionally, on the ARM, it can run several different tasks at once, kind of like threads, in that they can all operate at the same time, speeding up the application. For an example of how our ARM code is structured, I have a diagram up here. And what happens is sensor data comes in from the rover, it goes to the sensor task, which analyzes that data. It takes an average of the sensor readings and determines how best to react to what the sensors are seeing. And that data is then sent via message queue to the motor task. The motor task looks at that sensor data and makes an interpretation on whether it should continue going straight if it's already going straight, if it should make a turn, if it should make a left or right turn specifically, or a very sharp left turn or right turn, for example. And it also can even say, maybe we should slow down a little bit, or maybe we should speed up, depending on what the environment in front of the rover looks like. From there, the information in the motor task is packaged up and then sent back to the rover so that the motors can create the appropriate response requested by the arm.
To help our rover travel through the course, we used infrared sensors to detect where the wolves were. On the side, we used 2 short-range infrared sensors to detect wolves that would be in front of us on the side. These sensors have a range from about 3 centimeters to 40 centimeters. We also used a IR on the front. This one was a mid-range sensor and has a range of 10 centimeters to 80 centimeters. Other sensors that were used were this RFID reader. We used this RFID reader to detect our RFID tags on the track. Each RFID tag has a unique ID on it. Using that ID, we would determine whether we should speed up. We were supposed to determine whether we should speed up, slow down, stop the rover, or turn in a specific direction. Initially, instead of the front mid-range IR, we were supposed to have an ultrasonic proximity sensor. Unfortunately, we were not able to implement this because of problems that we were facing with the returning signal. The way this ultrasonic works is by emitting an ultrasonic wave and waiting for the reading to come back, and that using the rising and flowing edge, you determine the time that it took for the wave to travel that distance. For our RFID reader, we used an Innovations ID ID20 model RFID reader. The data sheet said this RFID reader had a range of about 16 centimeters. In actuality, it was only about half that, at 8 centimeters. It read the frequency at 125 kilohertz from this RFID tag. The RFID tag had 64 bits in it, a header, data, ID, and a parity bit. Using the unique ID, we can identify which RFID was read, and based on which RFID it was, make a decision. The IR infrared sensors had 3 pins on them: power, ground, and the signal pin. The signal pin would return an analog voltage depending on the distance that the IR realized. The PIC would use the analog to digital converter to convert that into a 10-bit voltage value. Using the graph that was given to us in the data sheet, we could turn that voltage value into an actual distance in centimeters. The ultrasonic that we were supposed to use worked differently. It used sound to detect what was in front of it. It would emit an ultrasonic pulse and then time the time it took for that pulse to return. The way it worked was it fed power and ground to it from the PIC, and it had a bidirectional TTL pin. We would drive the pin high for 5 microseconds, and then after a hold time of about 750 microseconds, the TTL pin would show a rising edge. When the pulse would return, there would be a falling edge on the TTL pin. Unfortunately, the rising and falling edge were not this clean. After we drove it for 5 microseconds, after the whole time, the pin would continue rising and falling several times, and for a duration of about 1 nanosecond, which the PIC probably realized as noise. Therefore, we were not able to use the ultrasonic in our design.
In our project specifications, we were asked to create a prototype PIC that would be used in the final design of our rover and have a significant role in the final demonstration. The prototype PIC was completed, but unfortunately we were not able to include it within the final demonstration because of various problems with debugging with the prototype PIC, as opposed to a PIC given to us by the course. Now, there were several problems I had when I was designing this prototype PIC. The approach I took was first just get the PIC on the board, get the ports for programming with the PIC at 2 or 3, attach some debugging lights over here in red, yellow, green, get some basic resistors, and make sure that I can read ADC values correctly first. After ADC was being read properly, the next step was to add the I2C train over here, which needed a series of diode rectifiers, as you can see throughout the board. It needed a buffer chip for the data going through the I2C, and I also added a power switch for good measure. The I2C train was working properly at some point, but it was not able to be reliably tested or verified that it was working due to some issues in general with the I2C ribbon cable and just some wiring issues. After much debugging and looking through schematics and my own wiring on the prototype PIC, I was able to get everything to work properly at the same time, and from there it was just a matter of adding in some wires to identify the channels that we would use for reading the IR sensors and the RFID sensors.
The ARM will send motor commands via I2C to the motor PIC, and the motor PIC will translate whatever message it receives into a UART message, which will send it to a Sabertooth motor control. This Sabertooth motor control has a power, a ground, and a RX pin, which basically means the read pin for the UART. And so when the motor PIC sends a message to the Sabertooth, it translates on here and sends it to each side of the rover. And so these pins on the outside are basically connected to the encoders and the motors on each side of the rover. The motor PIC sends a packeted UART message, which includes an address, a command, a speed, and a checksum. This packet is sent to the Sabertooth, and which is translated to the motors. The encoders are mounted on the front side of the rover, in which I would have attached it to the external interrupts on the motor PIC. Unfortunately, we were low on time and were not able to implement this part of the project.
The last thing I'd like to talk about is the navigation algorithm we were going to implement on the ARM. Due to some timing constraints and some other factors, we weren't able to implement the navigation in time. However, the way the algorithm would have functioned would have allowed the rover to speed up when it notices several straightaways along the course, and it would drive faster when it knows it's going straight. And it would also be able to optimize its turning radius around curves as it recognized a curve. But like I said, due to some constraints, we weren't able to implement that in a timely fashion. All in all, to summarize, I'd like to briefly talk about the things that we can improve upon in the future and what we did well to some extent. We could have improved upon our communication system, making sure that the UART functioned properly and actually got our wireless XB modules running. We could have implemented our navigation. We could have certainly worked on getting the ultrasonic sensor running, but that was discussed already. And we could have also worked on making sure that the RFID sensor and all the proper sign task information and speed limit information was sent to the ARM and implemented. However, among the things that I believe we did do well, we managed to navigate the course with little incidences of crashing into walls. It can turn well, it moves and can react to its sensor data, and the sensor data is reliable. The rover itself and the software does not crash. It can run indefinitely as long as it has power. And overall, the software side of things was reliable. We just needed to improve on some of our algorithms and our data, as well as our communication, of course. I think that was the biggest thing we needed to work on. All in all, though, it was a good project, and I think we did a great job with it. And I'd like to leave you with some videos of our rover performing on various tracks.
Shout to all my lost boys. Shout.